Okay, very well, very good. So, good morning everyone and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today it is a pleasure to welcome Daniela Kraft from the University of Leiden in the Netherlands. Daniela did her PhD at the University of Utrecht in the Netherlands. This was followed by a postdoc at New York University in the US, after which she came back to the Netherlands. And for some time, she's now been at the University of Leiden. And today she's going to tell us about some of her work on self-propelled particles, which, if I'm not mistaken, is funded by an ERC grant. Okay, so before I hand over to Daniela for the truly interesting stuff, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. Second, in the interests of internet stability, can I ask all of you, except the speaker, of course, to mute your microphones and turn off your cameras during the seminar. If you wish to ask a question, then of course you're free to unmute yourself and turn on your camera if you so desire. So without further ado, it's over to Daniela for the seminar.
Yes, thank you very much, Paula, for the introduction. What I want to tell you about today is three cryptic words: slip, ypsotaxis, and synchronization of catalytically self-propelled particles. And indeed, as Paula was saying, this research has been generously funded by the ERC. So what am I going to talk about? And what you see here is a particle, a spherical particle. And if we play the movie, then you can see that it's moving. And what you can also see, there's a shadow on one side where now the arrow is, and that's a platinum coating. And what you cannot see is that the solution, there's hydrogen peroxide. And if we speed this movie up, then the particle, you see that's actually a self-propelled particle. It's a particle that's not just randomly wriggling around, but it's a particle that has a propulsion direction away from this platinum coating. So let me just show you this in a drawing. So we have a spherical particle that is actually considering of some sort of composite material, considers something in between a silica and polymer material. And we have coated with platinum layer, that's the shadow you saw. And this platinum is catalyzing a catalytic reaction of hydrogen peroxide, which is essentially the fuel. And through this catalytic reaction, this particle creates a surface flow, and that surface flow is what drives the particle forward. And here's just a depiction of this surface flow as was recently measured by Campbell. The nice thing about this system, if you want to work with active particle, is that it works very easily. It's very straightforward. That's how we got there. That's why I think many people also work with it. So this is one of the first movies that my student Stefania took. And what you see is various particles now not in focus, and that's what why you don't see this platinum half. And they move around, and it's very robust, as I was saying. So that's great. So she came very quickly and very happily telling me this works. Now, as you may see, I'm glossing over a little bit about over what causes the propulsion exactly. And the reason is that there are actually two mechanisms that are currently proposed for this propulsion mechanism. And there is a debate in the literature which one it is. On the one hand, there is self-diffusive, that is that the particle generates a gradient in chemicals that then creates a gradient in pressure, which creates the fluid flow. And that's the self-diffusive. Oh, what happened? And the other option is the self-electrophoresis, where there is ionic species generated that create a current that creates this pressure gradient and electric field, and hence the fluid flow. And as you can already see, one of the distinguishing features is that there is charged or non-charged species. And the current favor for the self-electrophoresis comes from that salt has a strong impact on the motion of such particles. So if you have a tiny bit of salt, the motion stops very quickly. So that is why people favor self-electrophoresis at the moment. But that's not what I want to talk about at this moment. What I want to talk about is that these catalytic microswimmers actually have very strong affinity for walls. And if you're familiar with microscopy movies, then you could have already seen this in the movie that I showed you, named today, in the movie that I showed you, is namely that all particles stay in focus. So they're not changing in height or they defocus or in any way. So they all are on the plane. And this was also shown more carefully by Simchen et al. And Das et al. In 2015 and 2016 respectively, where on the top you have like a barrier in the sample, where when the particles hit that barrier, they turn that direction and then follow it. And in the bottom, what you cannot see is that there is really a trench where the particle goes in and then just follows that wall. And here is the work that I will show and explain to you later from us. That is a cylinder post, and what you can see is that the microswimmer adheres to the post and then goes around it. It orbits it for a very long time. And so this strong affinity for walls has actually been known for a really long time. When I was at my postdoc at NYU, I was looking over the shoulder of Jeremy Palachi doing his now famous experiments on these photocatalytic swimmers, and he was showing me that they go up the chamber wall of the container that he was having them in. And the surprising thing is that people have looked very little into this, the effect that walls have. They do matter. There are some experimental indications for that. One indication is actually that people report very disparate speeds. So if you have such an active particle, you can measure the speed, and under very similar conditions, so the same material of the particle, the same coating thickness, the same fuel concentration, the same size, people report like speeds that vary from 3 micrometers per second to 80 micrometers per second. And this is actually one of the questions my student came up with when she started, and she said, like, you asked me to compare this with literature, but there is a very broad range of speeds that have been reported. And the only thing that could have varied in these cases is, for example, the wall. Then there's more recently, there's a report from Holterhoff et al. Where they looked at catalytic swimmers on different surfaces, and in particular on glass and gold, and they report different speeds. Now this is a little bit difficult because gold itself may catalyze the reaction, so there is little, the conclusions that you can draw from this are, you have to be very careful. And there's also reports that the speed decreases if you add polyelectrolyte layers on glass surfaces, and the more layers you add, the less the speed is, and here it's a bit more difficult. So the 140 is a thinner layer than the 300, and at the same powering condition, you get a higher speed if the layer is thinner. And of course, and this is the experimental evidence, there is various theoretical predictions depending on the model you put in and the assumptions you make. There is not only different speeds reported, but also different states, such as hovering and sliding, and or bouncing off the wall. So these observations motivated us to look into what the effect the wall has on such microswimmers. And the first question is, of course, do the walls affect the propulsion, and how do they affect the propulsion if they do? And the second question is maybe even more fundamental, is then how far away from the wall are they actually? And what determines this distance? So if I'm talking about passive colloidal systems, there is a framework longer time ago established about how passive particles behave in a gravitational field and how they manage their distance to a wall. For active swimmer, this is currently lacking. And then the final question you may ask, if the wall actually influences microswimmer interactions, because if you one day want to go towards phase behavior, how do they cluster, then you want to understand that better. And so this is the questions that I will address today in my talk. The first question, how does the wall affect their propulsion? Now, I hope I gave you a good motivation why we think that the wall affects the propulsion, but this is not how we got to research this question. Because my ERC grant is about reconfigurable colloidal matter. And what you see here on the left, it's an example of such a reconfigurable lattice system that we were able to make. And the dream of this project was to add active elements like little forces, little motor elements that allow us to actively reshape a material into a different form, or to create swimmers that have like a wiggling tail and thereby have different swimming behavior. And so we set out to make these particles and then integrate them in the flexible structures. But it turns out that while initially this worked very easily, so we were able to make active particles, right out of the box, the moment we try to combine them with the flexible structures, they stopped swimming. And the most striking reason was that we put them on a different substrate. So instead of having a glass substrate, we needed to have a polymer coating substrate, and they just stopped right away. And that at that time we thought, let's have a look at why this is interesting, and maybe we can solve it. And indeed, this led to very interesting insights, I think. So let me show you first how this looks. So these are 3 experiments. On the glass one, this is a polymer material, not a polymer coating, a polymer material, polyethylene, and a very often employed material, PDMS. And these are the same particles, the same size, same material, same coating batch of platinum. So it's really the same stuff. And we put it in 10% hydrogen peroxide on these 3 materials, and you can watch it move. And again, you may say, oh, they're just wiggling a little bit, and that's because they're pretty slow and heavy. But what you may be able to distinguish is that these are moving a little bit, and these are moving quite a lot comparison. So you see that these ones are actually moving fairly well. Now you can quantify this. I am just measuring the trajectories in 8 seconds for all 3 substrates. And what you then see is that the glass and the polyethylene, they look very similar in their sort of how far particles get in a certain time, but the PDMS is much, much further. So very clearly, it must be the substrate, and all the particles are the same. The substrate must be the origin for this very different speed. And we can, of course, quantify the speed, and then you see that for glass, it's about 1 micrometer per second, just like for the polyethylene. And for the PDMS, we get almost 3 times higher speed. And what I will report in the following, and this is a tiny detail, you may forget that, is I will report most likely velocities, because what we saw in our experiments is that we have a velocity distribution like this. So the most likely velocity is the peak velocity of such a fit. And we're not reporting the average, because the average would be somewhere here. So what causes this difference, right? So what is the physical chemical property that affects the speed? And the first thing I thought, coming from a passive particle background, is this must be something to do with charges, something that pushes the particle further away from the wall. And in particular, what would expect is that the speed scales with the setup potential of the surface, so the charge of the surface. And so what we measured is the setup potential and in millivolt. And what you see here is that the glass is very negatively charged, less so than the PDMS, and even less so than hydrophilic PDMS. So we can modify this further. And you see that there is no correlation with the speeds that we measure and the setup potential of the surfaces. The next thing we thought was what Holterhoff et al. Suggested as well, is that surface roughness plays a role. And in that case, the rougher your surface is, the higher the speed would be. And again, we look at these 3 measurements of the speed and look at the roughness. And the interesting thing you can do when you take a slab of PDMS is that you first measure what the speed is, and then you hydrophilize it and measure again, and you have the same roughness, but you have very different speeds. So it's not in our case, it's not roughness that contributes mostly. I'm not saying that these 2 factors do not contribute. I'm sure they do, they have to, but their contribution seems to be subdominant. So what is it then, right? What is it if it's not something that I would traditionally expect? What you have to remember is that there's a fluid flow going. There's a fluid flow driven by these gradients of solutes on the particle surface. And that fluid flow has to interact somehow with the surface that the particle is close by. And such a surface has a boundary condition for the flow velocity. This boundary condition is called the slip. And if you have a no slip condition, the fluid flow on the surface has to be 0. Whereas if you have full slip, the fluid flow can have a non-zero velocity at the boundary. And what that means, and that was our thought, is that we can create higher fluid flow velocities in the bulk if we have full slip conditions, because we have to we can go to higher fluid flow at the surface. And if you have higher flow velocities, then you have higher particle velocities. So if this is true, so how do you measure the slip? And now there is interesting, very useful work by Lideric Bouquet's group, and that relates this slip length on the surface to the contact angle that you can measure, the macroscopic contact angle. So all you have to do is put a tiny droplet of your solution on your substrate, take a parallel view image, and then measure the contact angle of this. And you can get the contact angle out, and hence you know the slip. And because the measurement we do is contact angle, I will report everything now in terms of contact angle. So my student got slightly nervous. I mean, she proposed it herself, and then she got slightly nervous to measure it, but she shouldn't have worried, because the moment she put everything, all the data on a graph, we saw that the velocity has a very clear trend with the contact angle of the substrate. And these are very different materials or different surface treatments. It doesn't really matter, because apparently that one parameter, the contact angle, seems to capture what the velocity does of the particles. And then, of course, the question is, how can we describe this? Is this picture that we have in mind correct? And for this, we got in touch with Joost de Graaf, and he designed a model for velocity of a diffusive radic swimmer. And he actually changed our picture a little bit. So he says, well, what you have is a diffusive radic swimmer, and we take that for simplicity. And we say that the gradients that this swimmer creates now have an osmotic coupling to the nearby wall, so not to the swimmer's surface, but to the wall. And because we know that the wall must have an influence. And then the solid gradients that are generated on that particle surface create a surface fluid velocity, so a flow along the wall. And that flow has to scale with this interaction strength between the solids and the wall. And it's already known how this interaction scales with the contact angle. So that's great. So we can just put these things together. And what we find is that the velocity should scale as 1 over this cosine of the contact angle plus 1 to the 3/2. And actually, if we put the fit in, which is only 2 free parameters, it works very well. And I'm also plotting it log here so that you see it's really a power law fit that works well. And so that's great, right? So that means that you understand something. You know that the particle actually generates gradients that not only interact with the particle surface and thereby create fluid flows on the particle surface, but they also interact with the wall, creating fluid flows on the wall, and which affects the velocity of the particle. And this can explain the disparate reports in the literature. So this 3 micrometers, 18 micrometers reports. For example, if you take glass and you treat it differently, you wash it differently to make it super hydrophilic, or hydrophobic, basically having 3 different contact angles, then the distribution of the velocity shifts from very low to very high. So that's pretty cool, right? You have the same materials, you just have different surface property, and you affect the microswimmers. Okay, so what we learned is that the microswimmer's speed is dependent on the slip of the nearby substrate. So you get some sort of, I'd like to call this macroscopic effect, because I can see it with the microscope of something that's actually happening in a nanoscopic layer. We only looked at catalytic propelled microswimmers, but I think any microswimmer that is close to the surface might experience this. And we could apply this, for example, for guiding particles, having specific areas where they accumulate or are retained longer, and we're currently looking into this. Now, I want to, when this is true, if the slip at the wall influences the speed, then the microswimmer must actually be really close to the substrate. And how close? And that's naturally the question we asked ourselves, and we also could ask at conferences. And it turns out there is no answer to this yet. This is, as I said previously, I think this is a very fundamental question. What sets the distance between the microswimmer and a wall? For passive particles that don't self-propel, it's very well known. It's a competition between buoyancy, so the gravitational pull, depending on the surrounding fluid, and the electrostatic repulsion between the particle and the surface. So if I want to change that distance between a passive particle and a substrate, I would naturally put in some salt, change the surface charge, or change the radius, and then I would affect the height. For active particles, this is essentially unknown. The reason why this is unknown is that the typical measurement techniques that one would use, such as holographic microscopy or total internal reflection microscopy, they don't work. And that has to do with the platinum coating that creates reflections and plasmonic resonances. So the best that is available in the literature at this moment is an estimation of that wall separation. And the way this was estimated by Juliane Simpson is by having a step in your substrate of height and then seeing if particles that by chance swim towards that step, if they can hop over it. And what they saw, so this is the step height and the crossing probability. And what they saw is that around, let's say between 400 and 100 nanometer step heights, particles are able to cross it. So that means that the distance they must be having to the substrate must be in that range. So how can we then measure it? Because I like to have a quantitative measure. And what you need to do is you need to look again at the motion of the particles. And this is something we realized while measuring the slip dependence of the active particles. So in the limit that you in a short-term limit where rotational motion doesn't affect, in a short-term limit, we can describe the motion of active colloids, so the mean square displacement, by two contributions. The first contribution is an active component, so as if there is just a v squared t squared displacement. And on top of that, there is a random thermal motion component, a passive component. And that is a 4 times the diffusion coefficient times delta t. Now, what you need to realize is that this diffusion coefficient is dependent on the height of the particle from the substrate. We actually know this very well from the passive case, because passive particles have a one-on-one relation between the diffusion coefficient that you measure, scaled with the diffusion coefficient and bulk, and the height that they have from the substrate. So if you measure the diffusion coefficient of a passive particle and you know its size, you know immediately at what height from the substrate it is. And we can do the same trick for our active particles. So if we measure the motion of active particles, we have an active component and this passive component, and we can fit the V and the D of the two components, and then we can measure the diffusion coefficient and we can extract the height. So this is how such a mean square displacement looks, including the fits, the lines that we did with this equation. And what you can then extract is the average diffusion coefficient. In this case, it's about 0.07 micrometer squared per second. We can then use the same table and just look up, given this diffusion coefficient, what is the height that we get out. And what we find is it's about 250 nanometers. So this method gives us a quantitative way of measuring microswimmer wall separation with good precision. This allows us then to address how do different parameters impact the microswimmer wall distance. And we choose the ones that we would have expected to play a role, such as salt, surface charge, and radius. Let me start by showing you what happens if you add salt. On the left, you see the passive state. So this is the diffusion coefficient in orange. And when you add a little bit of salt, you see the diffusion coefficient goes down. And the reason is that the height is dropping. So it's closer to the substrate, so it has more friction. This is, and the fits, the lines you see are fits that come from the buoyancy versus electrostatic propulsion model. And you see it fits quite well. Now let's do this for the active particles. So here you have the diffusion coefficient and salt concentration. And what you see is it stays the same at the same range. And that means also that the height is constant in the same range. This is very different from what the velocity does. The velocity actually very quickly drops with salt. I told you this before already. If we add just a little bit of salt, it quickly drops and at some point just stops moving. So the speed is salt dependent, and we can in fact fit this this behavior using like this sort of a term like this, but the height is constant and it's about 250 nanometers. Next thing, surface charge of the particles. We already have an indication that this might not be so important because salt also doesn't affect it, but it's proposed to be important for the self-electrophoresis model. So we varied the surface charge. We made particles with different surface charges and the same size. So it's not a difference in size of material. And what you see here is that even if you invert the surface charge from a negative surface charge to a positive one, the diffusion coefficient stays the same, and hence the height stays the same. And even the velocity is unaffected by this. So there is constant height and constant velocity, and that is roughly 240 nanometers. And what it tells you is that electrostatics play a subdominant role in determining the speed and the height. Quite surprising if you ask me. I mean, electrostatics as in, yeah, okay, charge as the salt does. And finally, we thought, okay, we have to do something where we know it affects the diffusion coefficient, and that is we're changing the size of the swimmer. So if we make them larger, the diffusion coefficient must be going down, and indeed it does. So we find that in our measurement, and we find what we would expect for that. However, if we extract the height from this, we again find that the height is constant. So apparently the diffusion coefficient changes just due to the size, but not because of the, it also drops its height. And that height is about 300 nanometers. And what it tells you is that buoyancy, gravity, plays a subdominant role for the height. Okay, so let me summarize this. This was a lot of data. So we add salt to solution, we find a constant height. We change the surface charge of the swimmer. We even invert it from positive to negative, and we find a constant height. And we change the size of the swimmer, and we find a roughly constant height. And if you look at all of these together, then you see that there is actually, in all cases, the height seems to be very robust. So there is a tendency to assume a constant height of about 270 nanometers. My student is Greek, and she immediately says, we should call this ypsotaxis. It's a tendency to assume a constant height above the substrate. So we term this ypsotaxis. Ypsotaxis is, of course, induced by the active motion. So if you're adding fuel to the solution, then the height quickly drops and then seems to saturate, which tells you that the additional fuel doesn't affect the catalytic reaction or the fluid flow. And in the other terms, if you add fuel, then the speed increases very quickly and then saturates. So indeed, this ypsotaxis, the constant height, is induced by the activity itself. What exactly is the origin of ypsotaxis? I haven't told you, right? So in passive particles, I say buoyancy versus electrostatics. In ypsotaxis, I just say I find the constant height. I don't have a good explanation. And in fact, we don't have a good explanation yet. There must be some sort of competition between the hydrodynamics flows that we're inducing and the osmotic contribution, the osmotic interaction with the wall. But how exactly that requires much more detailed theoretical work. However, our observations and together with the slip observation have some implications for the propulsion mechanism. As I told you previously, currently favored is the self-electrophoresis on the particle. However, this model would predict that the speed should be sensitive to the zeta potential on the particle, so the surface charge of the particle. And we saw that it's very insensitive. And so we put forward a different idea about what propels these particles. And we look back at the salt dependence that we found and that other people before us have established. And we have two terms here. And the first term, that's a term that is independent of salt. And this could be a self-diffusive phoresis on the particle in the bulk, or some non-avionic effects on the wall. In the second term, we don't interpret as a salt dependence on the particle surface, but as a salt dependence on the wall. And what then would fit here is an ionic diffuser osmosis. It has to be ionic because it's charged species. And what we think is happening is that this interaction of the charged solids with the wall creates this fluid flow that opposes the self-propulsion. So if the particle gets close to the wall, this fluid flow slows down that fluid flow that is created by the particle, and that is how salt actually affects the motion. So what would now, of course, be the most interesting thing to do from an experimentalist is to measure motion in bulk and in the presence of additive salt. And this is unfortunately very difficult because, as I told you previously, there's a strong affinity for particles with the substrate. So what I showed you in the second part is that we could measure the microswimmers wall separation from the diffusive component of the motion. And we find ypsotaxis, so a constant height, even if we vary salt, particle size, and surface charge. And again, what we find is that walls strongly affect the microswimmers and cannot be neglected. Because if this proposed model is true, then it means that the wall is actually slowing down the particle, not the salt. The final thing I want to show you is the question. So if the walls are that important for particles, then if particles are interacting, is that also interacting through the wall? Is the wall playing a role? And this is a bit difficult to do if you're doing it in 2 dimensions, because particles meet only occasionally. They have various orientations. And then you have this, for example, motility-induced phase separation, but then you're not so sure what it has to do with interactions. So we simplified the setup. We said instead of 2D, let's go to 1D. And to do this, we printed cylinders on the surface, and we had the particles moving around. And here you see a cylinder and a particle. And if I play the movie, what you can see is that the particle quickly finds the cylinder and then starts to orbit it. And this was truly like one of these Friday afternoon experiments. And my students came excited and said, you have to see this because it orbits already for half an hour. And indeed, this is a very short movie, but I was there, we watched it, we went to another part in the sample, we went back, and they were still orbiting. So this is a very, very stable situation. But this is not what they were most excited about. I will show you, I should tell you the speed is pretty constant, it's distributed, and it's also pretty constant in time. But what they were really excited about was this. If there was not 1 particle on a cylinder, but 2, they went on this cylinder and they went around and around and around. And as I said, we came back half an hour later and they were still going around at this sort of angle that you see here. So this is a very, very stable situation. And if you have, instead of 2, if you have 3 particles, they do the same. So they go around and around and around, and they seem to have some sort of synchronized motion. And if you change the post size, if you go to larger ones, they do the same. So this is quite striking. You have active particles that have a stable distance, that have roughly equal speeds and long retention time. So let's have a look at exactly what's going on. So for the first thing, what you want to do is measure, do they have actually equal speeds? And what I'm showing you here is the probability density of the speed for these 3 particles in this movie, particle 1, 2, and 3. And you see the speed distribution is exactly the same. So indeed, they do have the same speed. More surprising maybe is that the speed depends on the number of particles. I mean, I find this so surprising, but even more surprising is that the speed of the number of particles, it depends on the number of particles. So if I have a single particle, I can measure the speed distribution and I skip the gray one. And if I have 2 particles on that cylinder, they speed out, they get faster. We can also do this for 3 particles. And again, they seem to speed up with every added particle. So it shifts, the velocity, the speed shifts towards higher speed. So they cooperate, there is some sort of collaboration between them. And I suppose this has to do with hydrodynamics and theoretic interactions. I'll come to back in a moment. So what we thought is, can we measure more? Can we measure is this just chance? It doesn't look like this is just chance, because in the sample itself, we also have a speed distribution, and that's not necessarily Gaussian. So we can measure the distance between the arc distance between 2 particles and see if that is constant as well. And so this is the distribution that we measure. So this is the probability density function of the arc distance for 4 different samples, 4 different situations. And then we thought, okay, this is actually very interesting. So there seems to be some sort of preferred a distance that they're at, but there's also wiggle room. So it's not that they're exactly at this distance, but they seem to be able to move with respect to each other. And yet they have the same speed distribution. So if you then think about, if you're going into some sort of co-moving, rotating frame, right? You're moving with the particles, you're in a frame of reference. Then what you only see is that the particles are wiggling with respect to some equilibrium position, as if they're in an external potential. And if you're taking that perspective, even though this is non-equilibrium, then you could say, well, I can use the Boltzmann distribution to extract the potential energy, this activity-induced potential that the particles are in. And this is what it looks like. So then you see, indeed, they seem to be confined in some sort of harmonic potential, and that with a certain depth, that is a few kT. So they're pretty, compared to kT, they are well defined, confined, and the width of that potential varies a little bit. And what you can see here, there's at least a trend that the further away they are from each other, the further away the minimum is, the broader this harmonic potential is. So there seems to be less confinement. So this, I thought this was very interesting, and I went back to Joost de Graaf and I said, what's going on here? How can we explain this? And so what he said, well, what we can do is we can again say, we can make a crude model. On the one hand, we know that we have repulsion between two swimmers, and that's because they have a pusher type propulsion, so the fluid flow goes away at the poles, and that creates a velocity field like this, where he already took into account the vicinity of the wall. And then he said, on top of that, there is a long-range attraction due to the osmotic flows along the substrate that I told you previously about. And they should scale like a factor over r squared. And these kappa and lambda, they are scaling factors that can then weigh the different contributions from these two types onto the velocity. And so if we then plot the flow velocity as a function of the distance, then we find that there are fluid flow velocities, like there are distances where the fluid flow is 0. And it's actually stably 0, because if you go away from that, it pushes you back towards that 0 flow velocity. So this means there are stable positions in the distance between two particles where they can move together. Okay, and that's induced by the fluid flows of the particles and the osmotic contributions. And this are not a stable distance, depends on these relative contributions from these two, from this phoretic flows and hydrodynamics. And that can explain the confining potential that we saw. Now, in the last few slides, I want to show you a few, just a few other lighter cool things, I think. And that is, besides the co-moving particles, you could of course also have particles that move in opposite directions. And this is a movie of when this is happening. And what you see then, the two particles are pushing and they're wiggling a little bit on the substrates, but they're essentially stuck. Now, if you take a random substrate, and I'll show you some different shaped ones in a moment, what can happen is some sort of tug of war. You already see it, right? So there's two particles pushing, but because they're pushing in the opposite directions, they're immobilizing each other. So if you have two particles like this, they become immobile. Interesting and unexpected, if you would have asked me beforehand, if now a third particle comes in and encounters such an immobile cluster, it also becomes immobile. I would have said, well, if you push in one direction, three particles, they should move in that direction, but they don't. And we've seen this several times. So this is also immobile. Only when there is a fourth particle coming in and there is a sort of extra, like two particles more than the ones pushing in opposite directions, then the cluster is mobilized again and starts to move. And I want to show you a movie, and I'm going to show you the movie on a different shaped post, on a peanut shaped post. And you have to watch here. So this is this peanut shape, that's the post. And here two swimmers, and they undergo this, they move in opposite directions, so they have a tug of war right now. And here comes in the third one, and I should just, whoops, I should just stop the movie. But you see the third one coming in, it comes from here, and you would have expected it to move the cluster, but it doesn't. And it comes in the fourth one, and there's equal balance. Only when this whole range of other particles come in, it's pushing the train forward and moving again. And what you also saw is that when we have these larger posts, we get chains to assemble. And so I'm going to show you some funny stuff with these chains. They have very dynamic and complex behavior. For example, they can reorganize, they can assemble, disassemble, and break up. And on the left movie, I want to show you this is a very nice chain. Then the first particles suddenly leave and they go around and then of course close at the end. So what you see is here it's moving, and here they come back again. And you see this chain is nicely following the substrate curvature. And because it has curvature, at some points it sometimes stops or it loses some particles. I don't want to tell you more about that yet. And but what you see, it's really nicely going around. And yeah, there's particles entering. Occasionally one, you saw here one coming in, but there's still a majority that pushes it and it still can move. And what I also want to show you is that particles can leave. So there's of course particles moving in both directions. And when they leave, they typically leave at the high curvature points, either negative or positive curvature. So maybe I can show you this movie once more when there's a particle leaving. So here now there's high curvature points here and here. And you saw this particle just escaped, and there's just a particle that escaped. I just show it once more. You saw that? Yeah, so it's at this high curvature points that particles are typically leaving the chain. And the chains can also break up. So this is a chain that moves first this direction, then comes in another one that immobilizes it, and another one. And that starts to rearrange things and get to more efficient flow. So it starts to move. Then it breaks up because it gets stuck at this corner. They like to get stuck at points of high curvature. It continues to move. So now it has four, it can move more easily. And it gets stuck again at the corner. And then it moves again. And then they will merge with this shorter chain. And then it can remobilize in the other direction. So what it just tells you is that this dynamic behavior is determined by the directions of motions of all the particles in your chain. Interestingly, this is really the last note I think I want to make. If you measure again the interparticle distance in a chain, that depends on the position. So this is the front of the chain. They're more closely together, and at the end you can already see here visually there's a larger distance. And if we measure this distance at the end, and it actually is the closest approach we've ever seen for two single particles on a spherical post. So there seems to be some preferred distance for two particles, that the closest they can approach. And then if there are more particles in there, they can approach closer because they can more efficiently create more efficient flows, I suppose. So in this last part, I showed you that a combination of this hydrodynamic repulsion and phoretic interaction across the wall can lead to activity-induced interactions between microswimmers. And we actually find some sort of activity-induced potential where we have confinement and the minimum. And these interactions create stable distances between cool moving particles, a cooperative speed up, so if there's more particles, they move faster, this tug of war or balance of power, if you want, and this very dynamic chains. Where we want to go next is we want to have models that not only are interesting from a non-equilibrium point of view towards applications, but also to use them as model systems for biological swimmers, and they're currently already used for that. And one of the things that you notice if you look at this comparison between biological swimmers and active particles is that they have in common that they propel, right? But there's also a difference, and that is the shape is vastly different. So we've now explored this new method of 3D microprinting to create particles of all kinds of shapes and make them active, such that we can explore the effect that shape has on their motion and their collective behavior. And here you see the movie of a little boat that swims, and I'm going to just speed it up so you can see the movement of that boat, and you see that it makes little circles as you would expect for this anisotropic shape. So this is the end of my talk. I hope I showed you that walls matter. I asked 3 questions. Do walls affect microswimmer propulsion? And the answer is yes. And it seems that wall slip is the dominant factor for speed. Then we answered, how far away from the wall do they swim and what sets this distance? And we found about 270 nanometers for our swimmers, and we found that this distance is very robust. So they have some tendency to stay at that height, in which we termed ypsotaxis. And finally, does the wall influence microswimmer interactions? And yes, it does. It does through these phoretic and hydrodynamic effects that are affected by the presence of the wall, which leads to very rich cooperative behavior. And if you take away one thing from this talk, then is that walls matter and you shouldn't neglect them. I'd like to thank a few people, in particular highlight Stefania Cazzezzi, who's done all these experiments in her PhD, and really has done a tremendous work here. Also like to thank Melissa Rinaldin and Rachel Doherty, and various other people in the lab that have contributed to this. And I'm really indebted to Joost de Graaf, who's done all the theory and helped us navigate the different propulsion mechanisms. If you want to know more, here are the publications that you can have a look up. One is still on archive and in review at this moment. And of course, I'm very happy about the funding through the ERC, which made this possible. We took a slight turn from where we wanted to go, but I think it is very interesting work nonetheless. And I thank you for your attention. I look forward to your questions.
All right, thanks very much, Daniela, for a truly exciting talk. Now, are there any questions from the audience? If there are, please raise the little hand. So we have a question from Margarita.
Yes, I'm unmuted. Hello, Daniela, thank you very much. A lot of information, very interesting, but in both parts, at least in the ypsotaxis and also in the synchronization, did you try to change the viscosity of the fluid? I mean, if hydrodynamics plays a big role, what happens if you change the fluid viscosity?
This is a very interesting suggestion. We haven't tried that yet, no. I think that's I would have to also think how to do it, but I recently came across some papers that do it. Yes, no, we haven't tried it, but you're right. This would be an interesting suggestion.
I mean, if hydrodynamics is important, you should try something like that to check. And also, it's sort of related, but in the second part, when you had the synchronization and does the distance between the particles and the angle they make when there are two, I mean, does that matter at all? I mean, is the speed different? How do you, do you have any control on how the particles sit, if they are sort of at some sort of acute angle or if they are on opposite?
No, so that is one of the things that that I find, that is still open, I would say. So if it, for example, right, you see here they have, so where does it go?
Oh, even in the circular.
So they have some sort of,
yes,
right, you have some sort of angle, and I think, sorry, go ahead.
No, I was saying I saw some.
So did they make some?
No, go ahead.
Okay, so basically what I think is going on is that they randomly attach in a random angle from each other, and that's somehow seems to stabilize. There only seems to be a minimum distance at which they can be, and once that is stabilized, they have a sort of wiggle room around that position, and the further away they are, the more wiggle room they have in this stable position. So that is what I can tell you.
They seem to change a little bit sometimes, and they seem to take different.
Yeah.
And that does not
exactly. That is what that. So they have wiggle room. So if you look here, this is the probabilities distribution of the distance. It's actually quite some wiggle room. So especially if they're further away, there's more wiggle room. If they're closer by, it's more confined. But still, the speeds are the same, and there's no there's no large changes in the distance.
I don't understand that at all. But anyway, do you have any explanation?
No, it's cool, right? I mean, this is what we see in experiments, and it's very surprising. And I think, we have some rough idea, but there's still a lot to do to understand it thoroughly. Yeah,
the range and the change are even, I mean, those I don't even dare to ask any questions. But anyway, thank you very much. Nice talk.
Say again? That you don't ask a question?
The chains, I mean, I don't even have questions. I think
the chains. Yeah.
It's even more complicated.
Yeah. So basically, I
don't have questions.
I mean, the chains is what okay. I think it's just the chains happen as soon as you have a stop. So there was a bit little time to go into that. So normally they seem to keep a distance, and there's a minimum distance, but when there is something immobilized, like two particles pointing in opposite directions, or at points of negative curvature where they get stuck, then you start to be able to make these chains. So where they really are in contact with each other, and then move together depending on which direction they're pointing at. And that is very dynamic, because now you have a chain moving, but in the chain, something might point the opposite direction. And at some point, by a random fluctuation of thermal motion, it can escape. And that's what you see that happens mostly at points where curvature varies, like at high curvature and low curvature points.
Okay, thank you. Thank you. I didn't want to take all the time for questions. Thank you.
Thank you very much for the interest.
Right, thank you. We have a question from Nuno now.
Hi, Daniela, thank you for your talk. My question is related to the dynamic chains. So one of the things that you analyzed was the distance between the particles as a function of the position in the chain. And I was wondering, how do you define the direction? And before you were also saying that the curvature plays an important role, but you said nothing about the curvature. Though it changes as you go through the chain in the example that you were showing?
Okay, no, I didn't. Okay, maybe I didn't say that correctly then. So let me see, let me just move to that thing. So curvature actually, okay, wait, give me 1 second. I'm just gonna go to another slide that I've skipped over a little bit in the beginning. So actually, oh, it's not here. Okay, it must be in a backup slide. Yes, sorry. I think you can see the slide now. So if we look at the speed as a function of the post diameter, so we actually looked at different post diameters or curvatures, if you want to invert it, we saw it surprisingly constant. So the speed itself, just on a spherical thing, doesn't seem to be affected, but the chain often stops at this curvature. So I'm not. Yeah, tell me. I don't know what this is, and especially if you have negative curvature points, which is not in this plot, you can actually stop the particle. Let me, in 1 second. And like this. So basically, if you have a particle coming in and it hits a negative curvature point, it's pointing down and it can't escape it, right? So it's getting stuck in that, and then it can start to assemble chains. And now your question was on the position in the. So indeed, we're not taking into account different the curvature differences here, because yeah, no, we don't. Yeah, it may play a small role. You're right.
So, what about the relative orientation of the different particles in terms of where the poles are pointing towards? Because even in the example of the negative curvature that you just show in the concave shape, I don't know if the colors that you use, the color gradient, is something to do with the poles of the particle or the orientation of the particle.
Yes, indeed. In the schematics, this is meant to be the poles of the particles. Yes.
Okay.
So basically, this is where the platinum is, and this is where the non-platinum side is. So that's the motion direction. And so from these movies, it's impossible to tell visually where they are, but you can infer it from the motion direction. Right, so you can see if you look at like this, and you know, okay, they must be pointing like in this direction. And in fact, the orientation such a particle has with respect to the wall, so the direction of motion, seems to be very stable. So there's earlier work by Das et al. 2015, and they showed that it's pretty stable with respect to the direction that it's pointing at. So once it's there, we don't expect it to flip over. So it's really stable. And it's also what we see when two particles hit each other that point different directions. They just stay there for a really long time.
But wouldn't that justify why they stay longer in regions where you have a negative curvature? Because
yes, it does. Yes, it does. Let me show you this. Oh, okay, I have to move out of this again. It does, because it moves in, right? So and it has the director parallel to the wall, so it's moving into that trench, and then it's just hitting the wall. And what it has to do is, by random thermal fluctuation, it has to reorient before it can escape. And that is why it takes such a long time. I mean, depending on the curvature that you're putting it in, it takes longer time to escape from there.
And so just a follow-up question. Then you could somehow calculate what is the typical time that takes to go out of all these places as a function of the curvature, and try to see if you get some probability distribution of finding a particle along the contour of your object as a function of the shape, for example, no? Even for
yes, I think you could. Yeah, I think you could. Yeah. And I think that's, I mean, yeah, and what you also see is that these points of negative and higher positive curvature are the points where particles leave the chain. And it's typically the particles that move the other way, right? So because if a particle that points this way, but is pushed into the chain like that, then it can actually much more easily escape from that trench than the other ones are like pointing downward. They're stuck, but that the one that's pointing upward just has to wiggle a little bit and can go out then.
Yeah, so you could think about designing shapes to
yes,
rectify the motion of active particle. Yeah.
Yes, exactly. And we've been thinking, we've been thinking hard, and you can also guide the motion and control the interactions, etc. Look at 1D phase behavior, etc.
Okay, makes sense. Thank you.
Thank you.
Okay, thank you. We have a question from Zamaria.
So hi Daniela, thank you for your nice talk. I would like to ask you, I think it's a continuation of something you were telling to Nuno. So there is not much difference between the motion of a single particle in a plane and in these pillars.
That's correct.
Yeah, so
yeah,
the velocity is more or less the same. So because it doesn't depend on the curvature.
Yeah. Also, well, what you see, what I didn't show you is we also measure this. Is that if you measure, this is the free speed that the particle has before it attaches to the pillar, and then the speed that it has after attachment. And you see, there's a linear scaling, and it's almost a slope one. So there is a tiny fraction slower, but it's almost slope one. So if you have 8, you don't get fully to 8.
It just changes direction. It's just when it attaches to the pillar, it just changes.
It has to direction. What it does, it's confined to a 1D path.
Yeah.
And then its orientation is locked in some way. So it can't just move anyway, but it's going to follow that path.
Okay. Thank you. Very interesting.
Yeah. Thank you.
Right. Are there any more questions? I don't see any more raised hands. So I think this is it. We thank Daniela again for a truly exciting seminar. Daniela, thanks very much. Thanks to everybody for coming. And before we close, can I just advise you that next week's seminar will be on Tuesday afternoon, not Thursday, but on Tuesday afternoon. So thanks everybody and see you there. Recording stops now.